Hey everyone, welcome to the Maths Extension 2 lecture for the April lecture series here at Notes. My name is Leo and I'm going to be your lecturer today. Thanks so much for coming and joining in this lecture. So before we begin, I do want to quickly talk to you about Notes. So we are an educational company run by former students for students. Our mission, our key goal, is all about accessible education and helping you achieve your potential. And we do this by offering a plethora of resources, including these lectures that you are currently watching. So we've been running these lectures since 2015, and we've been doing them every year ever since. We also offer study notes, hundreds of free notes for your subjects that we have on our website that you can download, as well as a discussions page where you can sort of talk with your fellow students about your subjects, engage in sort of a discourse and a conversation about that, and ask any questions that you might have about not just your HSC, but also queries that you might have about uni and stuff like that, which you can get answered on these discussion pages. We have a YouTube channel with a bunch of videos across your subjects, and we offer newsletters, ATA calculators, articles, and lots of other stuff that you can check out on our website. In addition to this, if you do need that extra support, we also offer a few paid premium resources as well, including a tutoring program, TuteSmart, that we have, where you get weekly 1.5 hour live classes every week that comprehensively covers the entire syllabus. These classes are live streamed, so you can go to them from the comfort of your own home, but they're fully interactive and they're recorded as well. So if you ever want to go back to a previous class, you can go ahead and go back to previous lessons, or available on the TuteSmart website. We also offer a bunch of study materials that we publish, including course notes, topic tests, as well as text guides, where you can buy those from our bookshops. They're written by top students with top tips to help you get great marks. And we also offer Ed Unlimited, which is sort of our Netflix for study kind of digital subscription service where you can access digital copies of our study guides via Ed Unlimited, just for a really low monthly subscription. There are a bunch of offers which you can check out on our website. So I'm sure that if you're interested, you can look around this website where you're currently watching the lectures. There will be information up there for you. So also want to take this moment to give a shout out to our university sponsors. Without their support, these lectures wouldn't be possible for you. So just a big thank you to La Trobe University, as well as our other university sponsors, including RMIT, Deakin, UTS, and Macquarie University as well. So just a little about myself. So my name is Leo. I graduated in 2018. Wow, 5 years ago. Feels like such a long time now. And I was an all-rounder for the HSC and achieved an ATA of 99.45. So I've been working at Notes and at TuteSmart since 2019. So wow, this is my 5th year of doing these lectures and being involved in the company. So I did a range of subjects across humanities and STEM. So I did biology, business studies, advanced English, extension and extension 2 maths, modern history, and I also did music too, but I did my HSC for that in year 10 because I was an accelerant. So I did music too as an accelerated student. So yeah, I accumulated like 14 units across my HSC, and I really enjoyed maths. It was one of my favorite subjects for the HSC. And yeah, as you all know, as students who do Extension 2, you get a mark out of 100 for both Extension 1 and Extension 2, because you're not required to sit the Maths Advanced paper. I managed to achieve a mark of 99 for Extension 1 and also a 93 for Extension 2. So I'm currently studying a combined arts and law degree at the University of Sydney, which I'm really enjoying, despite all the tremendous amounts of readings that I have at uni. I'm also a massive Swiftie, so shout out to my fellow Taylor Swift lovers. I absolutely love Taylor Swift and her amazing music. So yeah, shout out to you guys. And I also enjoy cubing. Rubik's Cubes are fun. I can solve up to a 5x5. And also the video game Valorant, despite me being an absolute noob at the game. So, still fun for me. But anyway, enough about me. Let's talk about the lecture. So, around this time of the year in April, we're around sort of halfway through the Extension 2 course. So, I hope you guys have all been enjoying it. It is by far the most difficult course, I think, in the HSC. It's the most challenging maths course. Of course, obviously, it's the highest level that you can do. So it can be very stressful, but from my personal experience, it was tough, but it was also very rewarding as well. So it was rigorous, but also very rewarding. So hopefully everyone's being at least having a semi-positive experience in Extension 2 so far. Today's lecture is all about integration. So as you all know, the syllabus changed in 2020. So you guys are the fourth cohort to set this new syllabus. So they simplified a lot of the stuff. You guys only have, simplified in terms of reduced the number of topics you need to cover. So you only have 5 topics. So you got your proof topic where you learn nature of proof and further proof by mathematical reduction. So all that contrapositive, negation, implication, kind of stuff that you did with quantifiers and stuff like that. Vectors, where you looked at 3D vectors, complex numbers, where you looked at imaginary numbers and Argand diagrams and modulus argument form. And then you also have a calculus topic where this is the topic we'll be covering today, and also a mechanics topic. So they simplified a lot. In the old syllabus, they used to have like conics, where you looked at ellipses, hyperbolas, eccentricity, stuff like that, and also a volume topic, but then they sort of like got rid of a lot of stuff. So yeah, today we are focused on integration. We'll be covering this area from the syllabus. And from personal experience, for some reason, integration is very popular in terms of everyone's favorite topic. A lot of people tell me that their favorite topic is like calculus. So hopefully you'll find this topic fun. You've learned how to do integration in Maths Advanced. In Extension 1, you sort of learned further stuff to extend your skills, like integration by substitution and also integrating results that lead to inverse trigonometric functions. In Extension 2, we extend that even further by looking at even more techniques, such as integration by parts and reduction formulas. So hopefully you'll find this topic fun. So this is the game plan for today. For today, we'll try to touch base on basically all of the integration techniques you'll be looking at in Extension 2. So we'll be looking at integration by substitution. We'll be looking at how you can do algebraic manipulation to help you solve an integral. We'll be doing partial fractions. We'll be doing integration by parts. We'll be looking at trigonometric integrals and tips with like complicated trig results, as well as trigonometric substitutions. And finally, we'll be concluding by looking at reflection substitution as well as the reduction formulas, which is, I think, one of the classical Extension 2 staples that you might get in an exam. And afterwards, we'll be looking at exam tips, if we do have time. So let's just dive straight into the topics. So this is like a typical like 2-unit or 3-unit style question where they might tell you to like differentiate x times e to the power of x and then integrate x e to the power of x with respect to x. You can sort of, once you differentiate it and then hence find that integral, it's pretty easy once you've done the differentiation because you can actually use that to help you do the integration. If you don't know what I'm talking about, you can pause this video and go ahead and try doing it. You will see what I mean, why it helps. But in extension 2, you'll get stuff like, you just get an integral like that, and they won't give you any context with how to do that integral. Same with substitutions. In extension 1, you were always given the substitution, while here in extension 2, you are expected to come up with the substitution yourself. So, the interesting but sort of sad reality about integration is that it is a whole lot more complicated than differentiation, because in terms of the sort of techniques that you can do to sort of computate and perform integration. Like with differentiation, you just have stuff like the quotient rule, the chain rule, power rule, the product rule, and then it's relatively straightforward. Whereas with integration, you have a whole bunch of different techniques that you might have to apply in order to get the integral. So just some refresher, some background about the standard integrals. So you got, you know the power rule from Maths Advanced. You learned how the integral of 1 over x is the natural logarithm, ln absolute value of x. You learned how to integrate exponential and also trigonometric results. And in the new syllabus, they did sort of explicitly flag integrating a to half x, which is just going to be a to half x over ln a. In extension 1, you learn these results that give you inverse trigonometric results. But also, in the old syllabus from 2015 and earlier, they had these results on the reference sheet. So these, I think, were removed, so I don't think you can quote these results anymore. You can get these last 2 results by doing a trig substitution, which is something we'll be doing a bit later on today, but I don't think you can quote these results anymore because they're not on the reference sheet. This one comes from just knowing how to differentiate sec. But before the reference sheet was introduced in 2016, in 2015 and earlier, this was literally the only thing which students were given in the exam paper. Yeah, literally you only had a sheet of standard integrals and nothing else. No formula sheets, nothing. But then NASA decided to be nice and introduced a reference sheet in 2016. But as we all know, as Extension 2 students, like really you shouldn't be relying on the reference sheet. Most of the time, you should be so on top of the content you won't even need it. Like for myself personally, when I did my HSC, didn't even look at the reference sheet, I think. But anyway, the point is there is that so far out of all of these integrals, this is still only a very small family of integrals we can evaluate. So with more complicated stuff, we learned in Extension 1 techniques like integration by substitution, but it was still limited to sort of undoing the chain rule. I mean, as if you went to my Extension 1 lecture for the series, you might have remembered me talking about the chain rule type integration by substitution questions, where it's not really, it's kind of dumb having to use the substitution because you can just easily do it with the reverse chain rule. But yeah, it was still sort of, there's still limitations to what you can do with an integration by substitution. But so the primary focus for today's lecture is all about anti-differentiation. So we'll be looking at indefinite integrals, but remember that you can, everything we learned here can still be applied in other areas, like areas. Very punny. No, it can be applied to other sort of like, yeah, other sections of integration as well, at other applications such as areas and also definite integrals and stuff. But yeah, we're just focusing right now on the actual anti-differentiation process, so the indefinite integrals. So just a quick revision of integration by substitution, which you learned in Extension 1. So say we got an integral of x root 3x minus 2, like that. And you were told to find this integral using the substitution u equals 3x minus 2. You would just u be equal to the substitution given, differentiate, rearrange to convert all the x's in terms of u. So in this case, the dx here becomes a third du. And then you can integrate like normal, and afterwards you can just make x a subject. So you replace all the u's with x's again. So in extension 2, with integration by substitution, unlike extension 1 where they give you the substitution here, in extension 2 they might just sort of give you an integral like that, and then you'd be expected to try, like you'll be expected to be able to just solve it. So either using some of the techniques we'll be talking about later on, or just by coming up with your own substitution. So let's do this question now. So if they tell you to just find x minus 2, the integral of x minus 2 over 2x plus 1 over 3 dx, the important thing to keep in mind is that it's not often the case where there's only one substitution you can do which will get you the right answer. A lot of the times there are multiple substitutions that will end up with the same result. So don't stress about like making sure you find the exact substitution you're supposed to do. Although saying that, there are sometimes cases where one substitution gives you a much easier working compared to doing another substitution. So just by practice, you sort of gain an intuition or sort of like a feel of what the right sort of substitution is. In this case, I think what we can do is we can just replace the denominator, the thing inside the brackets, with a substitution. So let's see what happens if we let u be equal to 2x plus 1. So I'm going to differentiate with the substitution with respect to x, and I can see that this will give me 2. So therefore du is equal to 2 dx, and that hence, in order to make dx a subject, I just divide by 2. So dx is equal to du over 2. So if here I got an x in the top, so if I rearrange, I can say that 2x is equal to u minus 1, and therefore x is equal to u minus 1 over 2. So therefore the integral is going to become x minus 2, I get u minus 1 over 2 minus 2 over 2x plus 1, I get u cubed times, here we get the dx, which becomes du over 2, like that. So this, I can take out the half, so this is going to be u minus 1 over 2 minus 2 over u cubed du, and then I can multiply the top and bottom of this fraction with 2, so it'll be half u minus 1 minus 4 over 2u cubed du, and I can take out this half as well, so it'll be a quarter u minus 5 over u cubed, which will give me a quarter. This will be u to the power of negative 2 minus 5 u to the power of negative 3 with respect to u. And you can see this is quite an easy integral for us to do. So this will become u to the power of negative 1 over negative 1 minus 5 u to the power of negative 2 over negative 2. So it will become a quarter. This will be negative 1 over u. This will be positive plus 5 over 2 u squared, like that. So our final answer is going to be, wait, it's not our final answer. So when we expand, we get this, we can say this is 5 over 8 u squared minus 1 over 4u, and don't forget your plus c because it is an indefinite integral, and also you can't just leave it in terms of u, you want to convert back to your original you want to convert back to your original variable, which was x, so all the u's become 2x plus 1. So this will become 5 over 8 2x plus 1 squared minus 1 over 4 2x plus 1. Yeah, plus c. And you could expand the brackets if you wish. I'm not going to do it here. So yeah, you can see with this integral, here I came up with my own substitution. You can experiment and see what sort of substitutions you might be able to do. But in this case, this one worked out. So yeah, as you can see, if you do this process, you'll be able to get the answer that I got over here. Alrighty, so let's try doing this question. And this time we are working with a definite integral now. So let's see what would happen if you just get an integral like this, which is something that you might get in the HSC paper. They won't give you the substitution, unlike extension 1. So let's say we are asked to integrate from 0 to ln 2 e to half x times e to half x plus 1 to the power of 5 with respect to x. So what would happen if I let u be equal to e to the power of x plus 1? Well, when I differentiate with respect to differentiate u with respect to x, I get e to the power of x. So therefore, when I say du, I can rearrange to say du is equal to e to the power of x dx. And therefore, I get e to the power of x dx here, that becomes a du, and this thing inside will become u to the power of 5. So now we can just change our limits. Because it's a definite integral, our original limits were from 0 to ln 2. So when x is 0, e to the power of 0 is 1, 1 plus 1 is 2. And e to the power of ln 2 is going to be 2, 2 plus 1 is 3. So therefore, we can say our integral is just the integral from 2 to 3 of u to the power of 5 du. So we can just simply integrate like so, and therefore our answer is going to be 3 to the power of 6, which is 729 divided by 6 minus 2 to the power of 6, which is going to be 64 over 6. And this will give us, when we do that, 759 minus 64 divided by 6, going to be 665 over 6. So as you can see, yeah, you can you can see the difference here on the slides. What happened was the substitution was u equals e to the power of x, and then you still get the exact same answer, but here I came up with the substitution u equals e to the power of x plus 1. So here's an example of what I mean by it doesn't really, like, oftentimes you can just get the same solution using a different substitution. So there's no like sort of right substitution that you have to be focused on getting. Like, as long as it helps you simplify the integral, it's done its job. So here, get the same thing. But yeah, here I just let u equals e to the power of x plus 1 instead. Okay. But the thing is, this question, you actually didn't need to use the substitution in the first place. If you paid closer attention, you would have realized that this is just a reverse chain rule question, because this is a function, and there's a function inside, but the derivative of the function inside is just e to the power of x, which is already on the outside. So this is actually in a perfect form, which we can directly integrate using the power rule, because the function inside has its derivative multiplied on the outside. So what you could have done instead was just directly integrated this. So this would have been e to the power of x plus 1 to the power of 6 over 6. And you just plug in your limits and you get the same result. So just like this, just like I illustrated here, it's kind of similar to when you get a question like this, where you have a function cos with a function inside sine. We know that the derivative of sine is cos. So once that's on the outside, you can just directly integrate it and you'll get the integral of cos is sine, so you get sine of sine plus c. So that's a similar example. So keep your eye out, keep your eye peeled for any sort of reverse chain rule style questions. And you are allowed to use the reverse chain rule directly because your reference sheet for the new syllabus is literally given in terms of the reverse chain rule. So you can see all of these results are given in terms of the reverse chain rule, where if there's a function inside a function and the derivative of that function is multiplied on the outside, you can just directly integrate the entire thing. So it doesn't matter if it's a trigonometric function, if it's an exponential function, logarithmic function, whatever, reverse chain rule applies. So make sure you account for the fact that if you have a function inside another function, you want to make sure that the derivative of that function is on the outside before you can then directly integrate. Okay, so what about a question like this where you are asked to do the integral of 1 over 1 plus root x? Ask yourself, how could I do this? Well, the problematic aspect is we've got the square root here, which is kind of hard to integrate. So what if I make a smart substitution to somehow get rid of that square root? What if I let x be equal to u squared instead? So I can somehow get rid of that square root, because when we square something and we square root it, it will kind of go away. Let's try doing this. So I'm going to differentiate x with respect to u. So this will be 2u. So I can say that dx is simply going to be 2u du, like that. So, so my original integral 1 over 1 plus root x dx will become 1 over 1 plus the square root of u squared, and dx becomes 2u du. So this will be, I'll take out the 2, we'll get u over 1 plus u, like that. So we have, we got u over 1 plus u. Now, how can I integrate this? Well, what if I add a 1 to the u so that it resembles the denominator? But then I can't just add a 1, otherwise I'm changing the question, so I'm going to have to bounce that out by subtracting a 1. So here I haven't changed the question because the u, I just added a 1 and then I took away a 1 in the same step, in the same numerator, so I haven't changed anything. But why have I done this? Well, now I can just split the fraction. So this is 1 plus u over 1 plus u minus 1 over 1 plus u, like so. So this all cancels nicely and it will become 1. And here I will have minus 1 over 1 plus u instead. So now we can integrate this result. So this will be integral of 1 is u, integral of 1 over 1 plus u is ln absolute value of 1 plus u. And this will become 2 u minus 2 ln absolute value of 1 plus u plus c. Don't forget your plus c, otherwise you'll lose a mark because it's an indefinite integral and you want to account for any arbitrary constants. Okay, so we can see we have to remember to convert back to the original variable as well. So if you just left it like that, you would lose a mark as well, because remember, with any integration by substitution question, you have to convert back. So we said that x is equal to u squared. So you can, yes, technically u is equal to plus minus root x, but for the purpose of integration, especially like if you went to my extension 1 lecture when we did sort of changing limits that have square roots and stuff, for integration you can just keep you can just take the positive, so u is equal to root x. So this will be 2 root x minus 2 ln absolute value of 1 plus root x plus c. And that is your final answer, which you can see here is what we got here on the slides. So there is a typo here. This should be square root of x instead. So yeah, there's a typo there. It should be square root of x. So you can see with this question, they didn't give you a substitution, but you sort of intuitively came up with it because you kind of wanted to get rid of this square root here in order to make it in a form which is easier for you to solve. Now, can you remember what I just did here earlier, where I did this trick of turning u over 1 plus u into 1 minus 1 over 1 plus u? This goes into our next sort of technique we'll be talking about, which is clever algebraic tricks, like what I did here about adding a 1 and then subtracting a 1. So here's like a sort of a summary of sort of what algebraic tricks you might be sort of required to use in order to manipulate the integral into a form which is easier for you to solve. So you might have to add and subtract the same thing, which is equivalent to adding 0, which is what I did here. I added a 1, then I subtracted a 1. Might have to multiply and divide by the same thing. Completing the square is also another technique, especially when you have to do results that lead to inverse trigonometric results. Polynomial long division is also very useful, and also partial fractions as well, when you want to break up a more complex fraction into the sum of simpler fractions. Okay, so here's example of what, so we just looked at adding and subtracting the same thing. Let's take a look at an example of where it might be useful to multiply and divide by the same thing. So let's take a look at integrating 1 over e to the power of x plus e to the power of negative x, like that. Like this might be just an integral you're given in the exam, and you'll be expected to be able to solve it. So taking a closer look, this is the same thing as the integral of 1 over e to the power of x plus e to the power of negative x is 1 over e to the power of x, like that. So, we got a nested fraction kind of here. So something that might be useful is if we multiply the top and the bottom with e to the power of x. Because I haven't really changed anything because this is just the same thing as 1. But here I will get e to the power of x in the top, e to the power of x squared, and plus 1 over here. So yeah, we got e to the power of 2x plus e to the power of x over e to the power of x, which is 1. Now, if I left it in this form, it would be kind of, it might be a bit sort of difficult for us to solve, but you need to remember that e to the power of 2x, as I expressed it earlier on, is the same thing as e to the power of x squared. Now, you might be thinking that doesn't really help us, like what was the significance of that? Well, if you take a closer look, this is the same thing as e to the power of x over 1 plus e to the power of x. Now, the thing is, we know how to integrate 1 over 1 plus x squared because we know it leads to inverse tan x. But the thing is, here we have a function inside the function. But the derivative of that function, of the function inside, is going to be e to the power of x, because when you differentiate e to the power of x, it stays the same. And we notice that this thing is already being multiplied on the outside. So we can just directly integrate this thing and say this is going to be inverse tan e to the power of x plus c, like so. And that is our final answer. And this is because it was in the form that's given to you on the reference sheet, where you got 1 plus f of x squared with the derivative being already multiplied on the outside. So you can see we got this through this algebraic manipulation and then a recognition of the inverse trig result. So yeah, you can see it's going to be inverse tan e to the power of x plus c. So another technique that you might have in algebraic manipulation is completing the square. And this is a cool technique you can use when there are quadratics in the denominator. So you might have sort of an integral where there's a quadratic like that with like a function on the top, and you might have the quadratic within a square root. So the trick is you kind of want to use the adding and subtracting algebraic manipulation trick to sort of get the top to resemble the bottom, and afterwards split the fraction like what we did earlier, and then see if you can get the reverse chain rule. Manipulate it so that you can try to do the reverse chain rule, and then for the second one you want to complete the square and then use a standard integral for that leads to an inverse trig result. So that's kind of confusing when it's written out like that. So let's just look at an example, just sort of see how this is applied. So yeah, this works if so you can see if you've got a squared plus bx plus c, the derivative of that is 2a plus b. So you want to manipulate it so that the top has a 2a x plus b, because that's the derivative of x squared plus bx plus c, and manipulate it so that you can apply the reverse chain rule, and then you can complete the square for the second fraction. And that's only if there's an x term in the top already. So and this also is only when the bottom is irreducible, meaning it can't be factorized. So let's take a look at an example. So let's say we are asked to integrate x over root 6x minus x squared with respect to x. So notice how here in this fraction we have a square root. We've got a square root in the bottom, and we also have an x term in the top. So let's try to manipulate it so that the top has the derivative of the bottom. So within this, so there's a function here, but within the function is another function, which is 6x minus x squared. The derivative of 6x minus x squared is 6 minus 2x. So I'm going to have to algebraically manipulate it so the top resembles the derivative, so that we can apply the reverse chain rule. So what I'm going to do is I'm going to multiply by negative 2, first of all. But I can't just multiply by 2 without balancing out the fact I did that by dividing by negative 2. Like that. And now I want to get a 6. So I'm going to add a 6, but I'm going to also subtract a 6 as well at the same time. So I can not change the question. So this all simplifies just to what we had originally with x over root 6x minus x squared. The reason why I did that is, so now I can split this off. So this will become 6 minus 2x over root 6x minus x squared minus 6 over root 6x minus x squared, like that. Now, I can split the integral now. So let's just, on the left-hand side, not the left-hand side, on the left here, this will be the same thing as negative half integral of, this is 6 minus 2x. Notice this is already the derivative of the thing inside, so we can directly apply the reverse train rule on that. So we've got 6, so we got 6 minus 2x times 6x minus x squared to the power of negative half. So we can directly integrate that. Here, I can say negative half times negative 6 will be plus 3 over 1 over root 6x minus x squared, like that. Like so. So basically, I just split the integral into two integrals. So we've got this integral here, and then we've got the plus 3 over 1 over root 6x minus x squared. So this one we can directly integrate now using the reverse train rule. So we've got a negative half out the front, and this will be 6x minus x squared raised to the power by 1 divided by the new power. But then over here, we see we got a 6x minus x squared. So what I'm going to do is I'm going to try completing the square. So this will be, if I, so we got, this is the same thing as, if I add, so this is minus x squared minus 6x. If I factorized out that, I would need a plus 9 within that bracket in order to complete the square here. But because minus 9, if I did a minus 9, I also need to add a 9 as well in order to balance out the fact. So that I when this expands, it will become a minus 9. So I can't just pull out a 9 out of nowhere. I need to also balance out the fact that I did that. So you can see, yeah, if you want to double check, you can expand this and you'll see it will all simplify to 6x minus x squared. So remember, the way we complete the square, we look at this, we halve it, then we square it to tell you what number you need to add in order to complete the square. So yeah, when that expands, will be 6x minus x squared. So now this thing is going to be negative root 6x minus x squared. And this will be plus 3 times the integral of 1 over 9 minus x minus 3 squared. And the reason why we completed a square now is you can see this is a standard form that we know, that we learned in extension 1, because we know it will lead to inverse sine. So therefore, our final answer is going to be negative root 6x minus x squared plus 3 times inverse sine x minus 3 over 3 plus c. And that is our final integral for what we get when we integrate x over root 6x minus x squared with respect to x. And we can see, yep, that's exactly what we got here from the working. So it will be minus root 6 x minus x squared plus 3 inverse sine x minus 3 over 3 plus c. Okay, cool. So yeah, you can see the difference between extension 2 integration and extension 1 or advanced integration. It is a bit more complicated, you can say, with sort of the algebraic tricks you sort of need to know, and also a good working knowledge of your standard results that you have. So let's try this question now. Let's say we are asked to integrate x plus 1 over x squared plus 4x plus 13. with respect to x. So again, the same sort of guiding principles. We want to, first of all, notice that this thing in the bottom is irreducible. You can't really factorize that. So last time we had a square root, so it didn't matter if you could factorize it or not. But here we don't have a square root, so you want to pay attention and make sure this isn't irreducible. You want to make sure it's irreducible before applying this technique. Because if it is reducible, if it is factorizable, instead you'll have to use partial fractions. But here it's irreducible, so we can try using this technique. So the derivative of x squared plus 4x is going to be 2x plus 4. So we kind of want a 2x plus 4 in the numerator. So let's do some algebraic manipulation to sort of see if we can get the derivative on the top. So I can multiply everything by 2. So that will give me 2x plus 2 over x squared plus 4x plus 13. But then if I do multiply by 2, I need to also balance out the fact that I multiply by 2 by dividing by 2. But now I want to get a plus 4. So what I can do is I can say that 2 is the same thing as plus 4 minus 2. Yeah, so I basically converted 2 into plus 4 minus 2. So we can have a 2x plus 4. Yeah, so I rewrote the 2 as plus 4 minus 2, so we can have a plus 4 there. So now that we have this, we can split the fraction. So this is the same thing as half 2x plus 4 over x squared plus 4x plus 13 minus 2 over x squared plus 4x plus 13. Like so. And we can, I suppose, do what we did last time and just split it into two separate integrals. So we got half 2x plus 4 over x squared plus 4x plus 13. And here we can say this is minus integral of 1 over x squared plus 4x plus 14, because the half and the 2 cancels out. And don't forget your dx here. Okay, so this one is a direct application of the reverse chain rule. Notice there's a function here in the denominator. The derivative of that is 2x plus 4, which we manipulated to get at the top. So this is simply going to be half ln absolute value of x squared plus 4x plus 13, because it's an application of the form where you got f dash of x over f of x, where it's 1 over f of x, but the derivative is already being multiplied on the outside. Okay, so we got that. Here, we can do what we did last time. In order to simplify this, we can try to complete the square. So this is the integral of x squared plus 4x. In order to get, to complete the square, divide 4 by 2, I get 2. Square 2, the square of 2 is just 4. So I want a 4. But in order to get a 4, I can just split the 13 as a 9. I can get 9 out. So 13, I split it in the sum of 9 and 4. So I get the 4 I want here. So now this is going to be when I complete the square, I get 1 over 9 plus x plus 2 squared. Like that. And remember, with the inverse hand form, it's going to be a over a squared plus x squared. So I want the a here. So a in this case is going to be 3. So what I'm going to do is I'm going to have the 3 up here, but also divide by 3. So I'm not changing the question. So now my final answer is going to be half ln absolute value of x squared plus 4x plus 13 minus a third inverse tan x plus 2 over 3 plus c, using our standard results that lead to inverse tan. So you can see, yep, that's what we got here. We got, also what you can say here is you can, you can, actually this thing inside is always going to be positive. So technically the discriminant here is negative, which means that there's no, real solutions. And also it's a concave up, so it's actually going to always be positive. So you can actually remove the absolute values if you want. You can just leave it as round brackets, which is fine. But yeah, it's just the exact same answer here. So yeah, you can see the same principles, just slightly different, because instead of a square root where we got inverse sine, we didn't have a square root, so we got inverse tan instead. But yeah, just going to be careful with your algebraic manipulation and also manipulating it so that you get the standard form where you can apply a standard integral. Okay. So, the next algebraic trick I want to talk about is polynomial long division. So it's very useful for when you have the degree of the polynomial in the denominator being less than the degree in the top. So if you see a fraction where the top degree is higher than the bottom degree, you can actually use long division to help you do that. So for example, so this is just a really cool case where if it's possible, so that's why it says if you can, you might be able to make your division really easy. Because remember, we learned in junior school, I'm not sure, I learned this in like year 8 or year 9, but I'm not sure how, because I know different schools teach different content, I think, in the junior schools, so I'm not sure if you've ever done it, but remember that you can factorize x cubed minus 1 as x minus 1 x squared plus x plus 1. Even if you didn't do this in junior school, you would have done this in year 12 extension 2 when you did complex numbers, because you would have looked at a lot of divisions like that. So it's not just x cubed minus 1. Remember, you learned x power n minus 1 is equal to x minus 1 x n minus 1. Like, yeah, you remember that. So you learned this already in the course. But yeah, for x cubed here, there's also an x cubed plus 1 factorization where it was x plus 1 x squared minus x plus 1. So that was another thing that we learned at the same time in like year 9 when we did that. It's called the sum and difference of two cubes. Okay. But anyway, here, because we recognize there's an x squared plus x plus 1, what you could have done here is you could have just subtracted a 1 and then added a 1, so that when you factorize the top as this thing, it will cancel out with the x squared plus x plus 1 in the bottom to just give you x minus 1. So you could have done that, and then afterwards with this fraction, you could just complete the square like what we did, and then you can use the inverse tan result in order to get the final answer, which would have been this result. So instead of using reverse chain rule, you could have done long division here, and that would have been fine. But you could have also, if you didn't want to do that, you could just use direct long division. So if the degree of the polynomial is in the top is more than in the bottom, or if it's in the bottom less than the top, same thing of saying the same. Two different ways of saying the same thing. You could have just literally done long division. Like, you want to divide x cubed with x squared plus x plus 1. Well, we want to, this is the same thing as plus 0x squared plus 0x plus 1. So we want to multiply this with x. So we get x cubed plus x squared plus x. It will be minus x squared minus x. So we'll get minus 1. So this will be minus x squared minus x. So minus x squared minus x minus 1. So this will be minus 1. So yeah, this would mean that you could say that x minus that x cubed over x squared plus x plus 1 is going to be, remember we got your we got the quotient, so x minus 1. We got the remainder, minus 1, over the divisor, so x squared plus x plus 1. So you didn't even need to recognize this using the algebra stuff. You could have just directly did long division on this, and it would have worked out when you wrote it as in terms of the when you divide this with that, you get the quotient with the remainder over the divisor. Remember that form where when you learned about this in polynomials. Okay, so you could have rewrote that in terms of this, and then you could have directly integrated this using what we did here. Okay, so let's move on to the next method now. So what we've been talking about, I flagged to you guys, was when we had a divisor. I mean, not a divisor, a denominator that was irreducible, which meant it can't be further factorized over the real numbers. But what if you can factorize it? Well, as I pointed out earlier, you'd need to use a technique called partial fractions. So basically what a partial fractions is, when you use it is when the degree of the denominator is higher than the degree of the numerator. So remember, when the degree in the bottom is less than in the top, we can just use long division and simplify the fraction. But when degree in the bottom is higher than the numerator, you have to sort of use partial fractions. And basically what partial fractions is you're breaking down a complicated fraction into the sum of more simpler fractions. So basically, if you wish to find the integral of a polynomial p of x over q of x, where q of x can be factorized into linear polynomials or quadratic polynomials, then there basically exists like sub-polynomials which satisfies this identity, where basically it's a bit complex when you write it like that, but basically it's saying if you've got something like 1 over x minus 2 times x plus 3, there is a way of writing it so that you can simplify this fraction as something a plus something over x plus 3. So something over x minus 2, something over x plus 3. So you can actually simplify it as a sum of simpler fractions, where each new denominator is a factor that you had from the initial denominator, and you just got something in the top. And the rule is, if you have a linear denominator, a linear factor, the top thing will be a constant. It will have a degree 1 less than what you have. But if you had like a quadratic, like for example, something like this, you would have a polynomial 1 degree less. So you would have a linear on the top instead. So you could have, like, if you got like 1 over x squared plus x plus 1 times x plus 3, or something like that, you could have rewritten this as a sum of two simpler fractions. So this is basically the gist of what partial fraction is. You basically split a complicated fraction into a sum of simpler fractions where each denominator of the new fractions is a factor of the original complicated sort of fraction. So let's just begin with a simple case where there's no repeated factors. So there's no like x minus 2 squared or something like that in the denominator. So just basically factorize your denominator. So factorize your q of x into real and linear quadratic factors. So either linear or either quadratic. Then write your expression like that. Then if your denominator is quadratic, put a linear term in the numerator. If your denominator is linear, put a constant. So basically you just want to have the degree 1 less than what the denominator is. Then afterwards you can use either equating coefficients or substituting values, or you can use a combination of both these methods in order to find what the coefficients are. So a bit complicated when I just say it, but it makes more sense when you actually do it. So let's say you want to integrate 1 over x squared minus a squared. Well, we know that this can be factorized as 1 minus, using the difference of two squares. We can factorize this as x minus a, x plus a. So now we can actually use partial fractions to, so I'm going to split this fraction. I'm going to let it be identically equal to, so it's not like a normal equation where it's, remember with x plus 2 equals 7, this will only happen when x is equal to 5. So this is an equation. It's different from saying something like x plus 2 is identically equal to x plus 1 plus 1. Because this will always be true for all values of x. This thing is only true when x is equal to 5. It's only true for a certain value of x. This is an identity where x is always true, no matter which value you put it. So here I'm writing it in a different form. So I'm going to split it as the sum of two fractions, each one with a denominator which is equal to one of these factors of the original denominator. Because they are linear ones, I'm going to have constant numerators. So just like what we did here, I can now combine this into a single fraction. So you know when I write this in a single fraction, I will get this. And because the denominators are the same as each other, I know the top have to be the same as well. So I know that 1 must be identically equal to this thing, which is what's written here on the slides, but this is giving you more context behind how we got that result. So we split it as, we let it be equal to this sum of, we let it be equal to the sum of these two fractions. Then we combine it, and then we are going to, we see that because the denominators are the same, we are going to know that 1 is identically equal to a times x plus a, and b is equal to x minus a. So the way you figure out what a and b are is you can either use substitution of smart values, or you can simply you can expand it and then you can compare the coefficients. So let's do comparing coefficients, because I think here we do a substitution, which can be often faster, but I want to show you that you can still do it by comparing coefficients. So this is identically equal to ax plus aa plus bx minus ba. So I can group the like terms together. So this is the same thing as a plus b, x plus aa minus ba. So comparing the coefficients for, so I can compare coefficients. Notice that on the left-hand side, we don't have a term for x, which means that our a plus b must be equal to 0 because the coefficient of x on the left-hand side is 0. There's no x term. So we know that a plus b must be equal to 0. And also, we know that a minus ba, the constant term is equal to 1 because the constant term on the left-hand side is equal to 1. So now we can just make a and b the subject. So we can just solve these, we can solve these two equations simultaneously. So for equation 1, I can multiply that by a, so I get aa plus ba is equal to 0. So now I can just add these two equations together. So I can say 2aa is equal to 1. So therefore, a must be equal to 1 over 2a. And therefore, I can plug this back into equation 1. So I can say that 1 over 2a plus b is equal to 0. So therefore, b is equal to negative 1 over 2a. So therefore, I can say that, remember, we let this entire fraction inside the integral be equal to this thing. So therefore, we know that the integral of 1 over x squared minus a squared is the same thing as the integral of the coefficient. We said a is 1 over 2a. So this will be 1 over 2a times x minus a. And plus b is minus, so it'll be minus 1 over 2a x plus a, like that. So this actually works out, if I factorize out a 2a, it'll be an integral of 1 over x minus a minus 1 over x plus a, which is actually going to be 1 over 2a ln absolute value of x minus a minus ln absolute value of x plus a, like that, plus c, which is, what we got here. So that's how you would integrate 1 over x squared minus a squared. It will simply be this result. And we know how to do this using partial fractions. So kind of a complicated example to start with. I would have preferred doing an example where we didn't have a. Here we would have like an actual number, but here it's just a generalized way it works, even when we have like coefficients and not just numbers like that. Okay. So here, so you can see here I did it by comparing coefficients, but another way you could have done it was you could have made smart substitutions. So back in this stage here, you could have let x equals a, so that you get, that will cancel out. You get 2a is going to be 1, so therefore a is just 1 over 2a. Then you can substitute x equals negative a to get b is equal to negative 1 over 2a. So that would have been a faster way, but here it shows that both ways are valid. Okay, let's try another example now. So let's say we are asked to integrate 2 over x minus 2 times x squared minus 4x plus 5. So notice how this bottom is already in a factorized form, and also that the top has a degree. The degree of the top is less than the bottom. So the bottom degree is actually bigger than the degree at the top. So we can't use long division. We're going to have to use partial fractions. So just like what we've done here, we're going to let this thing be equal to we're going to rewrite it in a different form. We're going to let it be identically equal to the sum of two fractions, because there's two factors here, where we got x minus 2 because that's one factor, and here we got x squared minus 4x plus 5, which is irreducible, so that can't be further factorized, which is what we want, because if it could be factorized, you would be able to split it into 3 fractions instead, but in this case it's irreducible, so we could just leave it as a quadratic like that. Notice how this time, because this is a linear factor, the numerator for this fraction is a constant, but for this one, because it's a quadratic, we are left with, we want to put a linear numerator instead. So remember that the degree is 1 less than what it is, so we are going to let it be equal to that. And then basically what happens when you combine it into one fraction is the numerators, when you compare the numerators, you see that 2 is identically equal to a times x squared minus 4x plus 5 plus bx plus c x minus 2. So the way we can do this is you can do what we did last time in order to find what a, b, and c are. You can do what we did last time and expand and compare the coefficients, or you can do substitutions where you can substitute values of x in order to try to get a quick result, or you can do a combination of both. So I think for this question, I'm going to do a combination of both. So I can see easily if I substitute x equals 2, I can eliminate this entire thing quickly. So I'm going to let x equals to 2. So in the left, there's no value for x, so it just stays 2. So 2 is equal to a times 2 squared, which is 4, minus 4 times 2, which is 8, plus 5. And here we get, this is 0, so that entire thing, it goes away. So we know that this is going to be negative 4 plus 5, which is 1. So that is going to be a plus 0 is 2. So therefore, a is just going to be 2, which is lovely. So now we know that 2 is identically equal to 2 x squared minus 4x plus 5 plus bx plus c x minus 2. So now I'm going to expand and then compare coefficients. So this is going to be 2x squared minus 8x plus 10. And here we got bx squared minus 2b plus cx minus 2c. So now we can collect the like terms together. So for x squared, we've got 2 plus b x squared. So we've got x squared there. For the x's, we got minus 8, which is this one, plus c, x. And then we got the constant terms, plus 10, minus 2b, minus 2c. So here we can just choose which coefficient we want to compare to. So let's compare the coefficient of x squared. On the left, we don't have an x squared term, so we know that 0 is equal to 2. So we compare coefficients. So 0 is equal to 2 plus b. So therefore, we know that b must be equal to negative 2. And we can also compare the coefficient of x. So we know that 0, because there's no term for x, is going to be minus 8 plus c. So therefore, c is equal to 8. And you can also compare this one with 2, and you can just double check if it's right. So you can see 10 times minus 2 times minus 2. So 10 plus 4 minus 2 times 8. So 10 minus 2 times minus 2 minus 2 times 8 gives you, minus 2. So just double check I did the right thing. So 2x squared. So we know that 2a is equal to 2. So 2x squared minus 8x plus 10 plus bx squared minus 2b plus cx minus 2c. So our x term. So this is right. We got b is equal to -2, but to get c, if x is equal to 0, then 0 minus, so if we had let x equal 0, you could have gotten so if we had let x equals to 0, what we would have gotten is 2 is equal to, we said that a was equal to 2, so 2 times 5 plus 0 plus c times 0 minus 2, which would have been 10 minus 2c. So 2c would have been equal to 8. So therefore c is equal to 4. So what happened here when I was comparing coefficients, bx squared minus 2b. Okay, I think, yeah, I think I realized what happened. This is bx, and that is minus 2bx. So I left out an x here. So be careful. We got a 2bx. So that changes things because this will be minus 8 plus c plus 2b. And here it would have been, instead of a 2b, it would have just been 10 minus 2c. So you could have actually compared the coefficient of this with that. So you would have gotten 2 is equal to 10 minus 2c anyway, so which would give you c equals 4. So yeah, just don't make any silly mistakes like I just did, where when I expanded, instead of saying bx, where this should have been, yeah, minus 2bx instead of just minus 2b. So yeah, c is equal to 4 and b is equal to -2 and a is equal to 2. So here I did a combination of comparing coefficients and also substitution. So afterwards, you can then break down this integral into these partial fractions, and then this one you can integrate using ln. This one you can then manipulate to get the reverse chain rule, and then you can integrate it like so. Cool. So, yeah. So let's talk about what happens when we have repeat factors now. So, if you have repeat factors, what you have to do is, if we have ax minus b to the power of m in the factorization, you just basically add a sum of fractions up to that start with like just ax minus b up to that power of m. So basically it's a bit confusing. What I'm saying is, if you have like 1 over x minus 5 to the power of 4, what you're going to have to do is, instead of just having a over x minus 5, you'd do a plus b x minus 5 squared plus c x minus 5 cubed plus d x minus 5 to the power 4. So if you had a situation where you had like in here x minus 1 or something like that, you would let this be identically equal to all of these 4 fractions plus an extra fraction to account for this factor here, like that. So with the if you had a quadratic repeat factor, it's the same logic, but instead of having a numerator that is a constant, you would have a linear numerator instead. So this is kind of example. We're not gonna actually do it, but this is just to see it in action. So say we had x minus 1 squared. Say we had to actually integrate 125 over x minus 1 squared times x squared plus 2x plus 2, that entire thing squared. What you have to do is, because we have a repeat factor for x minus 1's, we start from x minus 1, sum up all the way to x minus 1 squared. So we've got two fractions for that. And here we've got this x squared plus 2x plus 2, the entire thing squared. So we have to start with it and then sum up to it squared. And because of the fact that it's a quadratic denominator, I would have to make sure it's a linear factor instead. Linear numerator. So yeah, then you'd break it down into that, and then you'd have to do some substitution. You'd have to do some manipulation to sort of figure out what A, B, C, D, E, and F are. So yeah, let's not do that. Basically, in the end, if you actually do attempt this, you would get this result. This thing can be broken down as the sum of that, and then you can try integrating it. So let's actually do a question now, like not as complicated as this previous one, but yeah, let's just do this one. So if you got 1 over x squared times x minus 2, here the repeat factor is x, it's squared, so we would go a over x plus b over x squared. So if this was x cubed instead, what you would have done is you would have let this be 1. It would have been a over x plus b over x squared plus c over x cubed, then a d for the x minus 2. But in this case, we have x squared. So we're going to let it be equal to a over x plus b over x squared plus c over x minus 2. Then we can put this all into one fraction, and then we can say that 1 is equal to ax times x minus 2 plus b times x minus 2 plus c x squared. So let's figure out what a, b, and c are. So you can do substitution. So let x is equal to 2. So 1 is equal to 0 plus 0 plus c times 2 squared. So therefore c must be equal to 1/4. And then afterwards you can expand and then compare coefficients. So you get that b is negative half and a is negative 1/4. So then afterwards you can just basically put that back into you could break this thing down into the sum of these partial fractions. And then when you integrate, you'll get this result, because it's much easier to integrate these individual fractions than it is to integrate this entire big fraction there. So yeah, we are running kind of low on time, so apologies if we couldn't go through the exact comprehensive step-by-step process, because I do realize that we are running short on time and we still haven't done integration by parts or reduction formulas and that other stuff, so we should make sure we pace ourselves. So just as a side note, with partial fractions, there's actually a shortcut known as the Heaviside cover-up method. We won't discuss it now, but if you're curious, you can check it out in, like, I think it was in the Fitzpatrick, or was it in another textbook? But search it up online on Wikipedia. There's like a cover-up factor where it's quicker to find partial fractions. But I don't think you're allowed to use it in the HSC anyway, because if they want you to show your full working. Okay, let's go to the next section of what we'll be talking about today, which is integration by parts. So integration by parts is really cool because it's sort of like an extension to technique that you learn that only you guys know, and Extension 1 and Maths Fast students don't know this technique. So it's kind of like a product rule for integration instead of Like, you know how we had a product rule for differentiation? Well, this is sort of like a product rule for integration, but not really a product rule. It's sort of like a modified version. So we know that when we differentiate uv, we get u dash v, or you can write it as v u dash plus uv dash. So basically what you can do is rearrange it so that you can get a new result, which is the integration by parts. So basically it's saying if you have an integral where you could express it as one of them is u, the other one is v dash, then you can, using a rearranged product rule, the integral of this is the same thing as u times v minus the integral of v u dash. So if you have an integration of two things, you just want to figure out which one is u and figure out which one is v dash. Then afterwards you can say that this is the same thing as uv minus the integral of v u dash. And this all comes from the product rule, and then we just rearrange it. You can see here I integrated both sides. I said uv is equal to that thing, and then I basically took this to the other side and then subtracted that. So basically it's on your reference sheet. This is what it looks like. So the thing is, as cool as this technique is, you should really try to save it as a last resort, because the thing, as I mentioned, it's kind of like the integration version of a product rule, but it's not really as easy and straightforward as just directly differentiating using the product rule. The problem with integration by parts is it's sort of troublesome compared to the normal product rule, because sometimes you might have to do it more than once, and you also need to be smart with which part of the integral you decide to be u and which part you decide to be v dash. Because as you can see, it doesn't directly integrate it for you. It just leads you to get another integral. You get uv, but you also get another integral. So there's a really cool mnemonic, a really cool rule of thumb that we Extension 2 students are taught in terms of which one you decide to be u. So the mnemonic is liate. So this is a really useful mnemonic because it tells you the priority of which one you should let u. So it goes log, inverse trig, algebra, trig, exponential. That's what liate stands for. So if you have a log function somewhere in a logarithmic function in the integral, you want to prioritize giving that one to be u. So this is the priority list. Second is inverse trig. Third is algebra stuff, so constants or polynomials. Then it's trig, and lastly it's exponentials. So you kind of want to keep liate in mind when deciding which one is u. So let's say we wanted to integrate x squared cos x, like that. Well, the thing is, using liate, which one has priority to be u? Well, algebra is on top of trig. So x squared is algebra, cos is trig. Algebra has higher priority. So we're going to let u be x squared. And we're going to let v dash be equal to cos x. So therefore, when we differentiate u to get u dash, we get 2x. And when we integrate v, it will be the integral of cos is sine x. So remember that the product rule goes, when we are trying to integrate this thing, we will get uv minus u dash v, like that. So therefore, the integral of x squared cos x dx is going to be uv, so it's going to be x squared sine x minus the integral of u dash v here, or you could say v u dash. So it's going to be the integral of 2x sine x. So you can see exactly that. Yeah, this is what we got over here. Now, the problem with this is, you can see this thing here is still, we don't know how to integrate that yet. We've got a 2x times a sine x. So this is what I mean by integration by parts isn't as straightforward as a product rule. Like with the product rule, you could have just directly applied it and you would have gotten your derivative. The problem here is we just got another integral which we're not sure how to integrate. So let's just try doing it again. Let's try doing integration by parts again on this integral. So I'm going to let u be equal to, because lineate algebra gets priority over trig. So u be 2x, v dash, that's going to be sine. So u dash will be 2 and v is going to be negative cos. So therefore the integral is going to be x squared sine x minus, we got uv, so it's going to be negative 2x cos x and minus the integral of negative 2 cos x, like that. So when I expand the brackets, I get plus 2x cos x. So this will be plus, but it will become minus 2 integral of cos x dx, like that. Okay, so now this is an integral we know how to solve, because we know the integral of cos is simply just going to be sine. So our final answer is going to be x squared sine x plus 2x cos x minus 2 sine x. And don't forget your plus c, because it's an indefinite integral. So ta-da, we just integrated x squared cos x using integration by parts. Note how we had to apply it twice in order to get the answer. So as the slides say, yeah, that's what your answer is going to be. It's going to be x squared sine x plus 2x cos x minus 2 sine x. And that's what we get when we integrate x squared cos x. Okay, we can now look at another example with integration by parts. And the cool thing about integration by parts is it allows us to find integrals of stuff we normally wouldn't have been able to find just by ourselves. Here, it's going to ask us to integrate inverse tan. So we don't know how to integrate inverse tan. Remember, we only know that integrating 1 plus x squared gives us inverse tan, but we actually don't know how to integrate inverse tan itself. So using integration by part, we can do that. So remember lineate. The thing is, with integration by parts, you need to split it into two things, the product of two things. So here we only have an inverse tan, but remember, you can say that inverse tan is just going to be 1 times inverse tan. So there's still actually a thing being multiplied. It's just 1. You can say it, you can write it like that, so you can apply integration by parts. Now, which one are we going to let be u? Well, remember on lineate, inverse trig takes priority over algebra. So we're going to let inverse trig be u. So we're going to let inverse tan be u. So therefore, for v dash, that must be 1. So when we differentiate u, we get 1 over 1 plus x squared. And when we integrate v, we get x. So therefore, applying integration by parts, I'll get uv. So it will be x inverse tan x from 0 to 1, because those are our limits, minus the integral from 0 to 1 of u dash v. So this will be x over 1 plus x squared. Now, the thing here, I can plug this in. This will be 1 times inverse tan 1, which will be 1 times pi on 4 minus 0. And here, this is nice because in the denominator, we have 1 plus x squared. The derivative of that is going to be 2x. We want a 2x here, so I'm going to force myself to get a 2x in the top, but I don't want to change the question, so I'm going to divide by 2 in the front. So I'm balancing out the fact that I added a 2x. So this thing will now become pi on 4 minus half. Oh, this is from 0 to 1. This integral will be ln absolute value of 1 plus x squared from 0 to 1, like that. So therefore, this thing is going to be pi on 4 minus half ln 2 minus ln 1, which is going to be just pi on 4 minus half ln 2. So yeah, ta-da, we just learned how to integrate inverse tan. Here, it comes together nicely after you use integration by parts. Oops. So yeah, with to follow Lie, you just have a 1, then you would just let u be inverse tan and v dash be 1, and then you can apply integration by parts in order to get your result, which is going to give you pi on 4 minus half ln 2. So yeah, integration by parts is useful, but it can be cumbersome sometimes, but in this case, this was pretty straightforward. So yeah, it's really nice because it is basically a rearranged version of the product rule that helps us to do integration. Okay. So there are some special integrals where you have e to the power of ax sine bx and e to the power of ax cos bx. There's a special method to do these integrals that outlined in the HSC Notes Maths Extension 2 notes book. So if you're interested, you can go either purchase a copy from the bookstore, or you can get an unlimited subscription and you can read a digital copy for that. So as you can see, you usually use integration by parts when you're dealing with products of functions, but do you always want to use it? Remember, okay, so what the slide is trying to say is don't fall in the trap of always resorting to integration by parts as your default method. It's useful, yes, but you should try to use it as a last resort, because sometimes there are, as you saw from the earlier questions we did without using integration by parts, there are other ways of dealing with them. And sometimes you might miss an easier way because you always just resort to integration by parts. So, for example, if you had an integral like this, x e to the power of negative x squared over 2, would you want to use integration by parts? I mean, yes, this is the product of two functions, but notice how here there's a function, the derivative of that function is actually going to be negative x. So what you could have done is here, just put a negative sign here, and then you get negative x. And then you can just directly integrate this entire thing, so you get negative e to the power of negative x squared over 2 plus c. And that would have been your final answer for this integral. Much easier using the reverse chain rule. So just be careful, make sure you read the question carefully when you're doing these sorts of questions. So it turns out there are a wide variety of trigonometric functions to integrate. So remember that when you differentiate sine, cos, tan, and sec, you get these results respectively as listed on the screen. So let's talk about our next area in integration, which is integrating powers of sine. So if we have like powers of sine and powers of cos multiplied together, the trick is if your power of cos is odd, pull out the cos and use your substitution u equals sine x. Like pull out one of the causes so you can get a cos dx. So when you use u equals sine x, when you get du dx, it becomes cos x, so du is equal to cos x dx. So pull out the cos and use u equals sine x. If your power of sign is odd, pull out that sign, then use u equals cos x. So basically, whichever one is odd, you can pull that one out, then use a substitution for the other one. It makes a more sense why we do that when we do a question. And afterwards, you can use like trig identities to help solve. But if you're not lucky and you don't get any odd powers, you might have to just use double angle formulas, like either the sine double angle formula or the cos double angle formulas by rearranging using that. But it can be brutal and it can be a bit of an algebraic nightmare. But sometimes you might get a question where it's in the context of a reduction formula, which will help in the third case. And we'll be talking about reduction formulas at the end of today's lecture. So let's look at integrating powers of sine and cos now. So let's say we got the integral of sine to the power 6, cosine to the power 5, x. So sine x to the power 6 times cos x to the power of 5. So in this case, what you would have done, notice how the cos x is the one with the odd power. So you can just break it down into, as listed on the slide, pull out one of them. So you get a cos x dx. So you get a sine to the power 6x. Then we're left with a cos to the power of 4. And then you can just use your substitution u equals sine x. So this will become in terms of u. Here, this is the same thing as cos squared x, which squared. So then you can just use your trig identities for that. So basically, and then when you do du dx equals sine x, you get that du is equal to sine x dx. So this cos x dx becomes a du. Then we get u to the power 6 times 1 minus u squared. And then afterwards, you can basically expand the brackets. And then you can integrate like normal, then replace the u's with signs. So that is an example of how we can integrate sine to the power 6x cos to the power 5 x, like you get this result. So yeah, this is an illustration. And of course, if sine was odd, you would pull out a sine and then you let u be equal to cos instead. So yeah, it's a really useful trick for when you have to deal with powers of when you have to deal with high powers of sine and cosine multiplied together. Okay, this is a classic, how we integrate tan. Well, this is pretty easy. Just remember that tan is the same thing as sine over cos. And remember that the derivative of cosine is negative sign. So we want to make sure we have a negative sign in the front. So you can put a negative, but also put a negative at the front so you're not changing the question. And then this is in that beautiful form we love where we've got 1 over f of x, but it's being multiplied with the derivative of the function inside. So you can directly, when you integrate this will become ln, absolute value of that function. So it's going to be here, negative ln, absolute value of cos x plus c. So how do we integrate sec? Well, there's a trick to this. It's kind of hard to integrate it without knowing the trick. But basically the trick is, if you're trying to integrate sec, the trick is you want to multiply with sec x plus tan x and divide by sec x plus tan x. So you're not changing the question. So these will cancel out. But this is the trick of what you have to do. The reason why we do this is because this will become sec squared x plus sec x tan x over sec x plus tan x. And the thing is, the derivative of sec x is sec x plus tan x, the derivative of tan x is sec x squared. So basically, this is also in the form of having f dash of x over f of x. Because the derivative of sec x plus tan x is simply just going to be sec x tan x. It's going to be sec x tan x plus sec squared x, which is what we have here. So this will actually give us, when we integrate ln absolute value of sec x plus tan x plus c. And that's how we integrate sec x. You just have to know this trick of multiplying the top with sec x plus tan x and the bottom with sec x plus tan x. So you can see it here. That's how we do the integral of sec x. And if we're integrating powers of sec and tan, same sort of guiding principle. So if your power of sec is even, you can pull out a sec squared and then use the substitution u equals tan x so that you can get a sec squared x. Because remember, the derivative of tan is sec. So you can do some manipulation with that. If your power of sec is odd, and n is also odd as well, you can pull out sec x tan x from the integral, then substitute u equals sec x, because we know the derivative of that is going to be sec x tan x. Otherwise, try to convert everything in terms of sec using this identity, then try doing integration by parts. But that's a really horrible case, which hopefully you won't get. So here's an example of what I mean by that. So if we're integrating sec to the power of 4 and tan x to the power of n, where n is a positive integer, here, because we know that sec is the power of sec is even, we can let u equals tan x. We rearrange to get du is equal to that. We pull out a sec squared x, or become that using that, and then you can just integrate like normal, and it will all work out like that. And it helps with this identity that the one with the tan is sexy, so 1 plus tan squared x is equal to sec squared x. And here's an example where they're both odd. So instead you let u equals sec x. So then therefore, when you differentiate, you get du is equal to sec x tan x. Then you can pull that out from there. And then you can just keep resolving it, and then you can solve it. And here, if it's just sec and it's all odd, you can try breaking it into 2 and then use integration by parts. So notice how we've strategically split it into sec x and sec x squared, because we know that we can integrate sec x squared quite easily. So in red, this is our v dash. When we integrate, it will become tan x. And here with sec, when that's going to be our u, so the u dash of sec is sec x tan x. So you can apply that, and then you can be on your merry way to, it will be sec x tan x times tan. So then you can keep doing that. So then once you get this integral, you're going to have to, you can change this in terms of sec. And what actually happens is you actually end up getting this sec x cubed again. So you actually need to take it to the other side, because remember we said we let I be equal to sec cubed x. So along our way of working, we got sec x tan x using integration by parts. We got a sec cubed x plus integral of sec x. Now the thing is here, this is going to be I. So it's actually going to be sec x tan x minus I plus integral of sec x. So you can actually take that to the other side. So you could say that 2I is equal to sec x tan x plus integral of sec x. And we just talked about how we integrate sec x. We simply we know that this is going to be ln absolute value of sec x plus tan x using the process I explained earlier. And then don't forget it's an indefinite integral process, so we can do a plus c. But in this case, we notice how here we got a 2i. So when we simplify I to get what, remember we let I be equal to sec cubed x. So remember, c is just any arbitrary constant. So you, for the sake of making your life easier, you could just do a plus 2c because it's just any arbitrary constant. So therefore, when you finally find what I is, which is integral of sec cubed x, it's going to be half sec x tan x. You can factorize it, or you could just expand it. So half ln sec x plus tan x plus c. So that you could just have a final c at the end. So yeah, this is your answer. Here on the slides, it's been factorized the half, but here I've expanded the half. But yeah, what's with this random plus c plus 2c? It's literally just as a matter of convenience. Remember, c is just any arbitrary constant, so you could make it whatever you want. Just so that when you divide by 2, it just is a nice c. So you can see this is a typical extension 2 sort of technique, where in the process of integrating, you actually get the original integral back in your working, which means that you have to actually take it to the other side so that you can actually get what the actual integral is. So sometimes when you integrate, it's also useful to use your product to sum identities that you learned from extension 1 in year 11, and that will help you integrate when you have sine A times cos A as well. So, or like cos A times cos B, sine A, sine B. So for example, if you're asked to integrate sine 3x cos 4x, just remember your product to sum identities from year 11, and then you can integrate like so. Another way you can integrate is, remember when you learn about the T formula in year 11 extension? Well, another application of the T formula is actually with integration, because you can actually use, if you have like an integral which has sine and cos in the denominator or something like that, you can just let t be equal to tan x over 2, then use your trig your T formulas to replace it, and then it will help you do the integral. So remember when you're differentiating that and you're making dx equals to 2t, always do everything from scratch. Basically, don't quote this result that you get when you use the T formula. So let's say we wanted to integrate 1 over 1 plus sine x plus cos x. So with respect to x, in this case, we can let t be equal to tan x over 2. And remember that it comes from this triangle that we could draw. So when we differentiate t with respect to x, we get sec squared x over 2 times 2, which is going to be, times half, I mean, because of the chain rule. So that's going to be half. Remember that sec squared is 1 plus tan squared. So I'm going to change the sec squared into 1 plus tan squared. So that's going to be 1 over 2. We said that t is equal to tan x over 2, so this is 1 plus t squared. So therefore, I could say that dt is equal to half 1 plus t squared whoops, I meant, yeah, this is dt over dx. That's going to be 1 plus t squared over 2. So therefore, when I flip it, dx dt, that's going to be 2 over 1 plus t squared. And hence dx is going to be 2 over 1 plus t squared dt. And now when I want to integrate this, I can simply change this all in terms of t. So 1 plus 2t over 1 minus t squared using the t formula, plus 1 minus t squared over 1 plus t squared. And the dx is going to be 2 over 1 plus t squared dt when I integrate. So that is going to be 2 over 1 plus t squared plus 2t plus 1 minus t squared. And that will cancel out. And I'm left with the integral of 2 over 2 plus 2t, which is going to be 1 over 1 plus t dt. And this is going to be ln absolute value of 1 plus t plus c. And remember that t is equal to tan x over 2. So this is ln absolute value of 1 plus tan x over 2 plus c. And that's how you would solve an integral like that, where you would have, when you asked to integrate 1 over 1 plus sine x plus cos x, you can just simply use the t formulas to help you do that. So it's a really useful trick for when you have like sine and cos being added in a denominator or something like that. So we are running short on time, so it's I'm going to have to sort of go through this content quicker than I would like to. But with these trigonometric substitutions, sometimes when we have like a square root of a squared minus x squared, or like x squared plus a squared or x squared minus a squared, a smart substitution you might have to do is using a trig substitution, because these will allow us to use Pythagorean trig identities to get rid of the square root. Because let's say if we had x equals a sine theta, this would be a squared sine squared theta, which would be when you factorize out of a squared, it'll be 1 minus sine squared, which will give us cos squared. So it'll be the square root of a squared cos squared, which will give us a cos theta, which is much easier than having to deal with the square root. So here's an example, and yeah, the same logic goes with x squared plus a squared. If you substitute x equals a tan theta, you get like a 1 plus tan squared relationship, which will give you sec squared. And yeah, so let's say we had an integral like this. If you let x equals tan theta, you know that this thing in the bottom will become sec squared, which will become just sec, and that will cancel out with the sec that you get in the top because of what you did when you did the substitution. And then you can then integrate it like so. If you wanted to integrate root 9 minus x squared, you can let x equals 3 sine theta, and then you can proceed to integrate like that. But remember, the original thing was in terms of x, so you want to be careful. You have to draw a triangle to remember that your relationship is that x equals 3 sine theta. So we know that sine theta is equal to x over 3. So you would just draw a triangle like this, where x is equal to opposite over hypotenuse. So this side is going to be 9 minus x squared using Pythagoras. So therefore, when you rearrange it, when you get your final integral, remember with the sign, that is double angle. You can use double angle formula, and then you can find a value for sine and cos. So therefore, your final answer is going to be this result, like so. And as mentioned on the previous slide, here, if you have to do sec, it's going to be kind of nasty with domain restrictions and stuff. But can have a look through these slides in your own time. You can read it more carefully because we are running short on time. Another really useful thing that you come across in extension 2 is reflection property. So basically, it's that if you integrate a function from 0 to a, that's going to give you the same result as integrating f of a minus x if you're integrating from 0 to a. So it's basically like I think it's like something like this area here is going to be the same as this area here. Basically, that's what happens. You can try experimenting with different functions, and this is what the reflection property basically says. And you can prove it using a substitution. You end up getting integral of 0 of a of f of a minus u du, which is the same thing as integral of 0 a f of a minus x dx. When you have definite integrals, you come across something called a dummy variable in integration, where it doesn't matter which variable you're working with. It's just basically saying the integral of this with respect to u is going to be the same as the integral of this with respect to x. If you're it's just a variable that you're using. The definite integral will be the same. So I would recommend having a look at this integral to have a look at the reflection property in action and how easy it makes life. Basically, if you're integrating cos to the power of 2020x over cos 2020x plus sine 2020x, looks really nasty from 0 to pi 2. But if you use the reflection property, you'll know that if you're integrating from 0 to pi 2, that's going to be the same thing as when you're integrating cos of the function of pi 2 minus x, pi 2 minus x, pi 2 minus x. What actually happens is this thing in the top, remember that sine and cos are complementary. So cos pi on 2 minus x to the power of 2020 is going to be the same thing as sine x to the power of 2020. So what actually happens is you get these two results for the integral, which give you the same results. So what you can do is you can add them together. So if you add this integral with that integral, you actually end up getting two of those integrals, but with the cos and the sine at the top, with cos 2020, sine 2020, with over cos 2020, sine 2020. So these things actually cancel out and just give you 1. And then you can therefore integrate it really easily and you get pi 4. So you can see it makes a really complicated looking integral much easier using this reflection property trick. Okay, so the final thing we have to talk about today is the integration by using reduction formulas. So these basically sometimes you have integrals that have really high powers and they can take forever to deal with. However, a reduction formula is basically when you generalize the case. For example, if you can say, for example, if I is equal to integral of sine to the power of 7x or something like that, if, like, for example, like if this is I7 or something like that, and you have a result that says when you integrate I to the power of n, you just get a certain result like cos nx minus I n minus 2 or something like that, you can therefore have a generalized case where you can then simply repeat the pattern over and over again to find the actual integral. So here's an example. Let's say in is equal to the integral of cos x to the power of n. You can prove that you can express this integral, the result of that is equal to cos n minus 1 times sine x over n plus n minus 1 over n I to the power of n minus 2. And then hence, using this reduction formula, you can easily find the integral of cos 5 to the power of x. Cos x to the power of 5, I should say. So there was a typo here, so be careful. The way we do it is we split cos n to the power. So what we do is in is the integral of cos n x dx. So what we're going to do is we can split it as cos x, cos n minus 1 x. So this is, so ignore that n minus 1, there's a typo there. So what we can do now is we can let u be equal to cos n minus 1x and v dash be equal to cos x. And now we can use integration by parts. So u dash is n minus 1 cos n minus 2x, but don't forget the chain rule. So it's going to be a minus sign multiplied to that. The derivative of cos is negative sign. And for v, it's going to be sine when we integrate cos. So this integral is going to be uv. So sine x is going to be cos n minus 1x times sine x minus the minus cancels out with this minus sign, so it will be plus integral of if I take out the n minus 1, integral of sine x times what's written here, n minus 1 times the sine x times we are doing this thing here. So notice how there are two sine x's. We got this sine x here with the cos n minus 2x, but then we also need to multiply with that sine x as well. So what you end up getting is you're going to get sine squared x dx like that. And the way you continue doing this is, notice how this is sine squared x. You can convert that in terms of cos. So this will be 1 minus cos squared cos n minus 2 x dx, like so, after you apply integration by parts. And then when you proceed, you will get n minus 1 integral of cos n minus 2x minus cos x. Notice how cos squared x times cos x to the power of n minus 2 will just become cos x. So when you break this up, this will be cos n minus 1x sine x plus n minus 1. Remember, we said that in is the integral of cos to the power of n. So when we integrate cos, just looking at this one by itself, when we split this up into two fractions, it's going to be in minus 2. And here we got minus n minus 1, another cos, integral of cos x, which is going to be in. Oh, this is n here. So therefore, I can now take this to the other side. I can take this to the other side, and I can say that n minus 1 in plus in, because remember on the left-hand side we got an in, is equal to cos to the power of n minus 1x sine x plus n minus 1 in minus 2. So therefore, we can factorize out in. So this will be n minus 1 plus 1, which will just be simply n. So on the left-hand side, it will be n is equal to this entire thing, which I have here. So therefore, we can say that in, we could just divide everything by n, is going to be cos n minus 1 x sine x over n plus n minus 1 over n I n minus 2 as required. So this is, you can see how recursive it kind of was in terms of you got the original integral and you had to take it to the other side after we did integration by parts. But now that we got this result to find cosine x to the power 5, or, yeah, this is the steps written. Just remember there was a typo here that was cos x. Once we've done that, to find cos x to the power 5, remember that's just going to be I5. So you just apply this formula. Just plug in n equals 5 here. So you get cos 4x sine x over, this should be, yeah, that should be 5 over 4 over 5. So there's a typo here, that should be 5 there. So just be careful. There's some typos on the slides here. But yeah, you could just plug it in, that will be 5. And then afterwards you get I3. And then to find I3, you could just apply the formula again, recursively, just plug in n equals 3 instead. And then you can just directly go from there. So you just use the form. This is useful. Now that you have this reduction formula, you can simply just apply it over and over again whenever you need it to help. Whenever you have a question where you need to have like high powers, you could use it to bring down the powers. Okay, so we are well and truly over time. So that brings us to the end of all the integration topics we'll be talking about today. So there are a few more integration by reduction formula questions, which you can have a look on the site in your own time. And just a word of advice, integration is sort of like an art form. It's all about finding the right technique at the right time. As you saw today, there are heaps of different techniques that we have that you can apply. It's about choosing the right technique at the right time. And that comes with practice and sort of gaining that intuition that you get from doing lots of practice. So practice makes perfect. So we do have exam tips, but we are running out of time. We are already over time. So you can have a browse through the slides in your own time. They are available on the website which you're watching this lecture on. So yeah, if you're interested in any of the other stuff that, if you're interested in any of the other things that I mentioned at the start of the lecture in regards to TuteSmart and AT Notes and what we offer, you can look around the website and there'll be more information about that. But yeah, on that note, that brings us to the end of the lecture. Thanks so much for staying till the end. Thanks so much for watching. And yeah, wishing you all the very best with your HSC. Extension 2 is very tough. It can be very challenging at times, but yeah, you can push through it and it'll be very rewarding at the end. But anyway, thanks so much. And yeah, good luck with your Year 12 studies.